Okay, so hi guys, and thank you for coming. So today, right now, we're going to do. I'm going to give you the second lecture on the mini course on cryptography, and again later today, Kwang and Cherry, the amazing two TAs, will kind of follow up with the homework. Okay, so last time, yesterday, we kind of I started kind of telling you about the magical aspects of cryptography. And one thing we saw is how we can generate kind of randomness out of thin air. That was kind of the first magic, where the idea was instead of, of course, we cannot generate randomness, but we can generate like pseudo randomness. And that's actually what allows us to do kind of cryptography. And today I'm going to show you another magical aspect of cryptography, and that's the notion of zero knowledge proofs, which today became kind of a big hype because it's used a lot and more in blockchains now. So that became kind of a very big topic. Only recently, Ethereum also started using it, so it became kind of very popular. Okay, so let's start. So again, the topic for today is going to be kind of zero knowledge proof. And more generally, towards the end of the lecture, I'm going to talk about kind of how it influenced kind of the evolution of proofs in computer science. Okay, so let's start. Sorry, let me just move this so I can see my screen. Okay, so what are zero knowledge proofs? What's the goal here? So the goal is really to construct, so we're in cryptography, we want to hide things. So our goal here is to come up with proofs that reveal no information beyond the fact that the statement is true. Okay, so again, I want to convince you that something is true. I want you to be convinced, but learn nothing about why it's true. Okay, can we do it? How would we go about doing it? So this is the notion that Gordatov, Mikhali, and Rakov tried to kind of tackle in '85. They won a Turing Award for it. And it seems like magical. It's like, in magic, you do things magic. Nobody knows how you did it, right? It's really kind of almost the definition of magic. I'm convinced you something's true, no information whatsoever. Okay, so actually, before I dive into it, I want to say I really enjoyed giving you the lecture yesterday. I loved your participation, and please continue that today. So again, just unmute yourself. I can't see, don't raise hands or anything because I can't see them anyway. Just kind of jump in and and just ask your question, say your comment, whatever. Okay. So the first thing I want to tell you is actually that's impossible. How can you give what do you mean no information? Give a proof with no information beyond the validity. I mean, a proof itself is information in the sense that you can verify it. A proof is valuable. It's some information. Maybe if I have a proof of a very important theorem, maybe I can sell it. You can't say there's no information in it because it has some value. Even if you don't kind of learn exactly, you don't understand it fully, you can verify it line by line. So it seems like you must learn something from a proof. You learned that here's a proof. So it seems like that really seems like impossible to say you don't learn anything. At the same time, let me try to convince you that it is possible. Actually, let me just give you a zero knowledge proof. Okay? So, on the one hand, I'm telling you, look, a proof must give some information. You can verify it, for example. You can see it's correct, and you can, possibly sell it. You can do many things with the proof. But yeah, let me give you a zero knowledge proof. So here's my zero knowledge proof. I have two pencils here. I want to argue that they're different. They're not the same. I know maybe from where you're sitting you can notice that they're not the same. Maybe you can't. Let me prove to you that these pencils are not the same. But I want to get, of course I can tell you, if you look carefully, this one has, I don't know, a dent or something that this one doesn't have, but that will give you information. I don't want you to learn anything about why they're not the same, just the fact that they're different. Okay, now here's me as a magician. I'm going to convince you that they're not the same. You learn nothing. Okay, so here's how I'm going to prove it to you. I give you the two pencils. Okay, you take the two pencils. I'm going to not look. You decide. I'm going to tell you this is pencil A, this is pencil B. I'm going to turn my head. You're going to decide if to flip them or not to flip them. Okay, I come back. I'm going to tell you which one is A and which one is B. Now, first note, if they're indeed different, I will know which one is A and which one is B. If they're really the same, I have no idea if you flipped or not. So I'm going to succeed only with probability half. Okay, and if we do it many, many times, repeat it 100 times, then with very high probability, like 1 minus 1 over 2 to the 100, once I'll be incorrect. And then you're going to reject me. Okay, you can say, you don't know if they're the same. I don't believe you because you made a mistake. Okay, so that's my proof to you. Why is it zero knowledge? Let's see, what did you learn? Okay, well, first of all, if we do it 100 times, and every time I'm correct, you're convinced that they're different. Otherwise, what's the chances that I'll succeed in all the 100 times to guess correctly, if you flipped or not, if they were the same? So after these 100 trials, 100 is just, assuming you think of like 1 over 2 to the 100 is like almost zero. After these 100 trials, you're convinced that the pencils are different. Now, what did you learn? So let's see. I gave you the 2 pencils. You switch or didn't switch. Now, what did you learn from me? You learned that, this is A and this is B. But you knew that. You're the one who switched or didn't switch. So you really didn't learn anything. The only thing you learned is that I knew what you already knew, which is A and which is B. So it's zero knowledge proof. You didn't learn anything. Okay, so now you should be kind of confused because I just showed you in this slide here that it's impossible. Yet I just gave you zero knowledge proof. So where did I cheat? Where did I lie? I still stand behind the argument that this is impossible. I cannot give you a piece of paper with a proof that is your knowledge, because that piece of paper is knowledge. At the same time, I gave you zero knowledge proof.
You kind of taught us how to do zero knowledge proof. So that is a kind of information.
So, sorry, can you repeat it again? I didn't hear you.
You showed us zero knowledge proof. So I can do more proofs like that. So that is a kind of information to me.
You're right. I did give you the information that the statement is true and I can prove it to you. But you really didn't learn anything about why the pencils are different. In other words, you knew the answers I'm going to give anyway. You knew my proof. You knew kind of my answers, A, B, A, B, A, B. You knew them. So you really didn't get any information. The only information you gave is that the statement is true and that I know that they're different.
But now I know that you have a way of saying this is A and this is B.
Right.
There is some difference and you have some information. And I know that you have some information.
That's true. That's true. So what you learned is that I know that these pencils are different. That's what you learned. But you didn't learn anything beyond the fact that I know that these pencils are different. But here I want to say, in this case, you did learn. You actually got something valuable. You got a proof in your hand. You can later go sell it. You can later, that's value. In my zero knowledge proof, you got no value, except knowing that you can say, oh, Yael Kalai, she gave me a proof. And even that, I can say, no, I didn't. So what's the difference? I want to say you learned, but you got no value out of it. You can't go later and sell my proof to anybody. I'll tell you, no, I don't know, actually. He's lying. So let me tell you actually the difference, where I cheated. And this again, remember yesterday I told you that cryptography is the art of overcoming negative results. This is really, happening over and over again in cryptography, and this is yet another example. So when Goldreich, Mikali, and Rakov, stumbled upon this negative result, what they did is they changed the model of the proof. Now, you know what? Why is the proof, for thousands of years, the idea of proof, they were studied in ancient Greece and thousands of years ago. And what is a proof? There's a huge field in mathematics, maybe it's kind of a little dead by now, but called proof theory. And And what is proof? What is a proof? A proof is always like a proof. You verify line by line, and at the end, you decide yes or no, accept or reject. And even in a computer science, right? What is the class NP? It's the language of all statements that have a polynomial size proof, that have a witness that can be efficiently verified, right? So it's all the proofs that can be efficiently verified. And what's a proof? It's like a string. What Goldach, Mikhail, and Rakov said, you know what? We're going to change the model. First of all, a proof can be attractive. If you remember my example with the pencils, our proof was interactive. I told you A, B. I gave it to you. I turned around. You decide switch, not switch. You gave them back to me. I told you which one is A, which one is B. It's an interactive proof. So a proof, now we allow interaction between the prover and the verifier. Moreover, we allow the verifier to toss coins. Right? So in the example with the pencils, I gave you, the verifier, the pencils with probability half. You switch them with probability half. You didn't. It's a randomized, your randomized kind of, your strategy is randomized. It's very important. Because if you were deterministic, and I knew if you switch them or not, I can cheat easily. I'll tell you, they're the same for me. I tell you this is A, this is B. I know if you switch or not, and so I know which one is A and which one is B. So it's very important that the verifier tosses coins that the prover does not know. And moreover, the soundness condition is different. So we use in cryptography and in complexity theory the term completeness and soundness for proofs. Completeness just says that if the statement is true, you can convince the verifier to accept. In my example, with probability 1, if the pencils were different, I can convince you always with probability 1. In general, we allow a little less than 1. I wrote here 2/3. I'm going to explain this choice of constants in a second. But the soundness says if they're different, no matter, for any cheating prover, P star, he's going to convince the verifier to accept with small probability. And here I wrote 1/3. Okay, what I want to say is this 1/3 and 2/3 are arbitrary. The only important thing is that there's a gap between them. And the reason it's the reason any kind of constants with gap is good enough is because at the end of the day, what we can do is we can repeat this protocol many times. Let me call it K. Think of K as 100 or 200, whatever. We're going to repeat it many times. And then I'm going to say, let's see how many times you were accepted. Okay? In this case, I'm going to say, if you were accepted, let's say half, more than half, I'm going to say, I'm going to accept you. If less than half, I'm going to reject you. And now the point is, if X is in the language, I expect that you should be accepted about 2/3 of the time. Okay, if K is large enough, we know of concentration bounds. I don't want to go into it. It's called Chernoff bounds. But we know that you're going to be close to the 2/3. Okay, so with very high probability, you're going to be accepted more than half the time, with very high probability. And if it's not in the language, you're going to be close to 1/3. So with very, very high probability, you're going to be rejected more than 1/2 of the time. Okay, because you're going to be rejected actually 2/3, or you're going to be accepted only 1/3. You're going to be accepted with very high probability. You're going to be accepted at most or less than 1/2 of the time. So the point is, these constants are pretty arbitrary. Okay, so you can have any constant in mind. You can put there close to 1 and close to 0. Okay, so now this is the notion of proofs they considered. And in this model, so first of all, any question about the model?
I have a quick question.
Yes.
According to completeness, the probability that if the prover has the secret, the probability that the verifier accepts it's just bigger than or equal to 2 or 3. That means it's possible that even if the prover has a secret, the verifier may not accept it.
Right.
Why is it not? Why?
So good. So actually, I want to say in most of our protocols, indeed, completeness is 1. It's the soundness that is not 0. Okay, but completeness often is 1. But we do have protocols where the completeness is not 1, and that's why it's defined this way. But you're right that it seems a little contrived. You're like, if you have a secret, why can't you convince? So actually, that's a good point. In most natural protocols I can think of, the completeness is indeed one, but it's not always one. So that's why people kind of consider this definition. And actually, it's funny that you're asking. I was debating when I prepared the lecture whether to put here just one because, it's more natural. And at the end of the day, I just chose to do the 2/3, 1/3 because, I wanted to be consistent with the literature. This is what's often written in the literature just to allow kind of for more general protocols. And because there are protocols out there that do have completeness less than one. And so I wanted to be consistent with the literature, especially if you're going to look at like lecture notes and so on. This is often how things are presented. But for this lecture, I think it is a good proxy. Just think of completeness as being one. Because the protocols we're going to see in this lecture do have one, and most protocols I can think of, completeness is one.
Do you have a named example of an interactive proof system with completeness one just to read about later?
Yeah, I'm going to actually, with completeness one, you're saying. Yeah, I'm going to show you right now.
Oh, awesome.
Okay, so here's so let me tell you first of all, before I give you the example, before I actually give you I want to say my physical example with the pencils have completeness one, right? So I know if they're different, I give you the pencils, you choose to flip or not to flip. I always guess correctly if you flipped or not, because I know what they're different. I know what is A and what is B, so I can always guess probability one. But I'll give you, this is a physical example, right? It's like, I want to give you a protocol that it's just converse, like bits going over we send bits back and forth, I don't have to give you pencils. So I'm going to show you that in a second. But let me tell you, soon after this notion was introduced, there was a paper that showed this amazing result, very surprising, that says any statement that can be proved classically, not with a zero-knowledge proof, like classical proof, like with a piece of paper, with a classical witness. So it has just like an NP. You can take any classical proof and convert it into a zero-knowledge interactive proof, assuming one-way functions exist. So we're going to remember yesterday we talked about one-way functions. I'm going to remind you what that is. But for now, forget about the one-way function. The theorem says that every statement that has a classical proof can be converted into a zero-knowledge interactive proof. That's pretty amazing. We convert any proof to a zero-knowledge one. And it seemed like, wow, really? How can you do it? You know what? I'm going to show you how to do it right now in this lecture. Okay. But before I show you how to do it, before I give you the example, first of all, how do we even define zero-knowledge? So essentially, the way I want to define, and by the way, before I dive into the definition, I want to tell you, look, I'm giving you only 2 lectures in cryptography, and I'm trying to cover kind of very deep and interesting aspects of cryptography. I don't expect, I think it's kind of impossible to really understand it all and to understand all the formalism. My goal here is not for you to understand everything in the lecture. My hope or my goal for this lecture is to give you intuition and hopefully to convince you that cryptography is amazing and that you should want to kind of take a class and dive into it deeper. Okay, so just for expectations. Okay, but with that, so I want to argue that there is zero knowledge proof. For that, I need actual definition. What do I mean by zero knowledge? So I want to say, really, zero knowledge says that essentially the verifier, he learned nothing. He knew what the prover was going to send him, right? Like in the example of the pencils, he knew if the prover was going to send A or B. So he didn't learn anything. He could simulate the prover in his head. He could tell you what the prover will send. That's essentially what we mean. It gives no information. And the way we formalize it is we say, essentially the verifier knew he knew already what the prover will answer or what the prover will tell him. We formalize this by saying that actually there exists a simulator, a PPT, probabilistic polynomial time. Again, we always think of efficient is polynomial time or probabilistic polynomial time. So there exists an efficient algorithm, S meaning simulator, think of the simulator as kind of the verifier that can predict the prover's answer. This simulator, he knows the statement that we want to prove. Let's say we want to prove that X is in some NP, in some language or whatever, that if we want to prove Fermat's theorem, whatever it is the statement, the simulator gets the statement. And he can actually, he behaves as the verifier, and he can predict what the prover will say. So he can essentially simulate this entire communication. He's saying, look, I know I'm going to give the prover that. I know what he's going to send me back. And then maybe I'll send him another message. I know what he's going to send me back. So he can kind of look, you don't learn anything because I can predict this entire conversation in my own head. So I didn't gain anything from the prover. I could predict what the prover will say in my head. Okay, so whereas before, when you had in the classical setting, I told you, oh, proof is information, because you can then tell someone, oh, look, Fermat's theorem is true. I have a proof for that. Look, you can verify it. I'm willing to sell you the proof, or something like that. Here, it's like, no, the verifier could do it. The verifier could do it on his own, or the simulator can simulate this on his own, like even if he doesn't have a witness, even if a witness almost doesn't exist in a sense. So that's what we mean. You don't get any information. You could have generated that on your own without actually knowing if the statement is true or not. Okay, and what I want to show you next is actually the example that you wanted of a zero-knowledge proof. And then when I'll show you the simulation, maybe you'll have more kind of a handle on what that actually means. But do you want to, let me stop for a second for questions, see if you have any questions before I proceed. Okay, so I want to prove to you that any language, any proof, any efficiently verifiable proof can be converted into a zero-knowledge one. So what do I mean by efficiently verifiable proof? I mean, essentially, again, in computer science, this is kind of NP languages. NP languages are the ones that have efficient proof. So I want to take an NP language, and I want to generate show that for any NP language L, I can prove to you that X is in L using a zero-knowledge proof. And the way I'm going to do that, so I assume you guys know what NP is and NP completeness. Actually, if you don't know, it doesn't really matter. But what I'm going to do, I'm going to give you an NP proof for a specific problem, the graph three-colorable problem. And I want to argue that that's enough. If I give you zero-knowledge proof for that, that's enough because this is an NP-complete problem. So any language in NP, you can convert it to a three-colorable graph so that instance in the language, if and only if the three-colorable graph is in the language. So it's enough to give proofs for three-colorable graphs. Okay, but again, those who don't kind of forgot of the theory of NP completeness and so on, then I'm just going to give you a proof of three-colorable graph. So what is a three-colorable graph? I'm going to give you a graph, and I want to argue that you can color the vertices. So a graph just has a set of vertices and a set of edges, and it's three-colorable if you can color all the vertices in three colors. Let me call the colors 1, 2, and 3. Okay, so I can color the vertices in colors 1, 2, and 3. Think of when 1 is blue, 2 is red, 3 is green. Doesn't matter. I'm going to color in three colors such that any two adjacent nodes, any two adjacent vertices have different colors. Okay, if the graph has such a coloring, it's called a three-colorable graph. Okay, now here I have a graph. I'm a prover. I want to convince the verifier that this graph is indeed three-colorable. So I have a coloring in my head for this graph. Okay, I know how to color the vertices in colors 1, 2, and 3, so that each two adjacent vertices are colored in different colors. But I don't want to tell the verifier the coloring. I want it to be zero knowledge. Of course, I can give the verifier the coloring. He can check. But I don't want him to get any information. I want it to be zero knowledge. So now to the example, let me tell you let me give you the zero knowledge proof. Okay, so here it goes. So any question about the problem first? Okay, so here's I want to prove to you that this graph is 3-colorable, and here's what I'm going to do. First, I'm going to randomly permute my coloring. But when I say randomly permute, all I mean is I rename my colors. So let's say I have a coloring, that colors with colors 1, 2, and 3. Every place that I have color 1, I'm going to replace it with a random color between 1, 2, 3. And so I'm going to call 1 another color, let's say 2, call 2 another color, let's say 1, and 3, 3. Or I'm going to just permute the colors randomly. Okay? So now I permuted them randomly, and I have a new coloring. I'll explain why I permuted them randomly in a second. If at this point it's annoying to you to think about it, forget about this step. Okay? I'll explain this later. So now I have the coloring of the vertices. Let's say the number of vertices is n. I have the coloring C1 up to Cn. Each one is either 1, 2, or 3. And what I do, if I didn't care about hiding, I'll just send you the C1 up to Cn, the colors, and you can check. But I want to hide. So I'm going to send it to you, but inside kind of hidden. So let me first use kind of, again, a physical device, and then we're going to use cryptography to get rid of it. Okay? But for now, let's say I'm going to give you physical safes. So I'm going to give you the colors, but inside an opaque box that you cannot open. You need a key to open. I'm not giving you the key. Okay, so far you didn't learn anything. You got n boxes with no keys. So you learned nothing. Okay, and again, in the first box, I put color number 1, second box, color number 2, and so on and so forth. Then wait. Okay, so far you learn nothing. Okay. Then what the verifier does, it chooses a random edge in the graph. So let's say 2 vertices, right, I and j. And he tells the prover, I want you to open. Essentially, he sends in the edge, which essentially tells the prover, I want the keys to the ith box and the jth box. And the prover needs to give it to open the safe. He needs to give him the 2 keys to the ith safe, or I box, or safe, I safe and jth safe. And then the verifier opens the safes, and he checks that the colors are legal, are both between 1, 2, and 3, and that they're different. Okay, and if so, he accepts. Sorry. Okay, this is the protocol. So first of all, is the protocol clear? Okay, I'm sending you all my colors in locked safes. They're opaque. You ask to open 2 of the safes. You choose a random edge, and that defines 2 safes that you want me to open. I give you the 2 keys. You accept if the colors are distinct and between 1, 2, and 3. Okay, so let's see. First of all, let's see. First, we have completeness and soundness. We'll talk about zero knowledge in a second. For completeness, yes, of course, I'll put the colors, my coloring in there. You ask me to open, I'll open. They're valid because my coloring is good. So probability 1. Okay, so back to the example that was requested. Here's an example, completeness 1. Okay, I always succeed. What about soundness? So now suppose I don't have a valid coloring. Can I still convince you to accept?
So then there's a certain chance, just if we didn't know the proof, we would guess the correct coloring.
Okay, so great. So, okay, there is no true coloring, first of all. So you can't, even if I didn't, suppose the graph is not 3-colorable. It's just there's no way. For example, if the graph has a clique of size 4, so 4 nodes that are completely connected, you can't color it in 3 colors. You need at least 4. So if the graph is not 3-colorable, okay, so for example, if there's a 4 clique hidden somewhere, or there are other examples, of course, of graphs that you cannot color in 3 colors, then there's no way I can. Okay, I'm a cheating prover. I'll put whatever colors I want here. But I know it's not a legal color because a legal coloring does not exist if the graph is not 3-colorable. Okay, so I'll put a coloring there. You choose a random edge. I need to open. What is the chances that I'll succeed in the opening here?
I mean, we might need to check all the safes and the final edge that is the one that invalidates the proof.
Great. So what you're saying is, you're saying, wait, maybe all the edges are good except for one edge. You know, the fact that it's not three-colorable, it can be almost. You know, maybe you can color it in a way that almost all the edges are good, but one edge is kind of problematic. You're right. That can be. And therefore, if he chooses the problematic edge, I'm dead. Then you caught me. But there is probability, 1 over the size of E, that he will choose the bad edge. So you'll still catch me, but with probability only 1 over the length of E. So the problem is the soundness here is very high. It's very close to 1. Completeness is 1, but soundness is also very high. So the only thing I can argue is that I will be accepted with probability at most 1 minus 1 over the number of edges. I know there must be at least one edge that, you know, kind of that this colors are that essentially is not legally colored. But perhaps there's only one edge, and then I will be caught with very little probability, or I will succeed with very high probability, 1 minus 1 over E. So it's like, oh, that seems like a very sucky proof. Like, really? That's pathetic. But don't worry, because what we can do, we can repeat this proof, like K times the size of E times, and then again, lower the probability, lower the soundness to exponentially small. So by repetition, exactly like we did with the pencils, we'll repeat this protocol many times, and if every time, much more than E times, like K times K times the number of edges times, and each and every time I succeed, now you're convinced with very high probability. Okay, so the actual protocol will be repeat this many times and accept it, you always accept it. Okay, and that's how the soundness probability goes down.
To be clear, we are going to have to permute the coloring every time, right?
Awesome, great. Okay, so now, right. So now, good. So the great comment. And now we're going to talk about zero knowledge, and I'll talk about the permutation now. But very good point. Good. So what about zero knowledge? Okay, is it zero knowledge? And now comes, that's where I need the permutation here, the randomly permute the coloring. So far I didn't use it, but now it's coming into play. So let's see. What did the verifier learn? Okay, he got a bunch of safes and learned nothing. Then he asked for a random edge. What did he got the opening of 2 safes. What did he learn? He learned 2 colors, 2 distinct colors. But what did I do before I sent the colors? I randomly permuted the colors. Because I randomly permuted them, essentially what he learned is what he sees in the safes are 2 random distinct colors. So essentially now you're saying he didn't learn anything. He knows what the answer will be. So let me tell you how he can simulate this proof in his head. Boxes, everything is black, edge, and then the opening is 2 random distinct colors. He knows there are going to be 2 random distinct colors. If you repeat it, it's very important to repermute. So you repeat it again. Black safes, like blocked, random edge, 2 random distinct colors. 2 random distinct colors. Every time 2 random distinct colors. Note, if you don't have this random permutation, or if you do it just once and you don't redo it again, you just keep like the same coloring, eventually all the boxes will be opened and then you learn the coloring. So really not zero knowledge. So to make it zero knowledge, every time you repeat this protocol, the prover will re-randomize his coloring. So he will rename the 1, 2, 3 randomly. And then every time what the verifier sees is just 2 random distinct colors, 2 random distinct colors, 2 random distinct colors. He learned nothing. He knows the distribution of the opening. Any questions?
Do we achieve the same effect if we permute the boxes or nodes other than permute the coloring?
So, okay, good. So permuting the boxes is problematic for the following reason. The verifier needs to know which box corresponds, like even for completeness in a sense, he needs to know which box corresponds to which vertex, because he needs to know if there's an edge between two boxes. So when he sends here, he says open box I and J, he needs to know that there is an edge between vertex I and vertex J. But if we permute the boxes randomly, he doesn't know now which box corresponds to which vertex. And if we tell him, then he can yeah.
All right, thank you.
Okay, great question though. Great question. Any other question?
If there exists, okay, I'll go ahead. If there exists only one valid three-coloring of the graph,
Yeah.
Will it still stay a zero knowledge proof?
Great. So I want to argue, even if there's a single three coloring of the graph, this is still zero knowledge. Why? What does the prover do? He has his single, okay, so actually, let me say it again. There is no unique. There can't be a unique. Why? There can be a unique up to renaming the colors. So in other words, let's say you're saying there is a unique color, coloring of the graph. I'm going to say if you take any color that's called color 1 and you replace it by color 2, and you replace every color 2 and replace it by color 3, and you take any color 3 and replace it by color 1, it's also valid. So if you rename the colors, it's still a valid coloring.
Yeah.
And this is what I'm using here. That's kind of, you're totally right. That's the fact that I can rename the colors and still get a valid coloring. That's really at the crux of the zero knowledge argument.
Mm.
So that's a very, very, guys, you have great questions. So that's exactly right. So because every time I'm going to randomly rename the coloring, that's what allows me to argue that when I open to two random distinct colors, no matter what I saw so far. So even if, so in other words, let's say the proven verifier talked once. Okay, the verifier saw the answers. They talk again, he saw the answers. They talk again, he saw the answers. Next time, still the answers are still going to be random distinct, independent of what he saw so far. And it's always because I can randomly rename and get a valid coloring.
I have a question, just out of curiosity.
Yes.
Say I'm an impatient verifier, and I'm like getting tired sending one edge at a time. Is it possible for me to reveal like more than a single, or like ask for more than a single edge, like other subgraph? I can imagine, like, obviously, if I ask for the entire graph, that's not a good idea. But what about like a tree or something like that? Could I get away with more?
Okay, that's a great idea. The answer is we don't know. Okay. Moreover, one can ask the following. I said repeat this sequentially many, many, many times. What if you repeat it in parallel? Like you're saying, look, I don't want to wait. Let's repeat the same thing in parallel many times. So, in other words, I understand that you don't want to reveal information. So give me n boxes, give me another n boxes, another, many kinds. And every time, yes, permute as you wish, okay? But give me the n boxes, another n boxes, another n boxes. Then I'm going to give you, for each n boxes, I'm going to give you a random edge here, a random edge here, a bunch of random edges, and you just open all of them. Why sequentially? Let's do it all at the same time, okay? So let me tell you, the question is zero knowledge. And let me tell you, this question was open for many, many years. Since the introduction of zero knowledge in the mid 80s, people didn't know, does it compose in parallel? Like if you have zero knowledge proof and you take it in parallel, so what did we do here? We have a zero knowledge proof, but with bad soundness. So we repeat to get a better soundness. I said repeat sequentially. Why sequentially? You're right. People don't like to, people are impatient. Let's do it in parallel. Would it work? We didn't know. Only last year came an answer to this question. And the answer is, it's not necessarily zero knowledge. If you take a zero knowledge proof and repeat it in Perl many times, it may not be zero knowledge anymore. It's unbelievable, like how complicated the proof of this theorem is. And also a bit counterintuitive, I think. My guess is maybe many of you, if I asked you, is it zero knowledge, you would say yes. By the way, Sherry, you're muted. I don't know if you're, okay.
No, just nodding along to let you know that I'm still here.
Okay. But let me tell you why, if you are surprised, let me tell you why you should be surprised. Because when I defined zero knowledge, I said that the verifier does not learn anything from interacting. The way I defined it, let me go back for a second. I defined it up here that essentially the interaction between the prover and verifier can be simulated. Okay, the verifier, he knows essentially what the prover is going to answer, or he knows the distribution of what the prover is going to answer. But actually, this definition that I defined here is what is called honest verifier zero knowledge. It's assuming the verifier is honest, he doesn't learn. But actually, when we talk about zero knowledge, we want to make sure, if we want to hide something, when we want to give a proof and make sure you don't learn anything, often, we use zero knowledge proofs a lot in cryptography. And we use zero knowledge because often we prove things about our own secret key. And so it's paramount to us that, we don't leak our secret key when we prove things. And we don't try, even if the verifier is malicious, we want to make sure that he doesn't learn anything. So it's not enough for us that the verifier that's honest and following the protocol doesn't learn. We want to ensure that even a malicious verifier who doesn't follow the protocol, he just wants to learn our secret or our witness, or he doesn't learn anything. And that's called a malicious verifier zero knowledge, or usually just zero knowledge. And there we consider also malicious verifiers. And when we do parallel repetition, zero knowledge does hold with respect to honest verifiers. It just doesn't hold with respect to malicious verifiers. So namely, there's a malicious verifier. There's a very clever strategy for a malicious verifier to deviate from the protocol in a way that he learns something, if you do it in parallel. Whereas if you do it sequentially, he can't do it.
Is that limited even if they make a polynomial number of parallel requests, or does it have to be an exponential number?
No, polynomial. Yeah. Polynomial number of parallel repetitions. If you do constant, it's okay, but then the soundness doesn't go down. But if you do polynomial, which is what you want essentially to get the sound, if you repeat it enough to get the soundness down, it's not, they're counter-exempt. I can come up with a malicious verifier strategy that learns. So that's pretty remarkable. So in the homework assignment, one of the homework assignment is about kind of how would you define malicious verifier zero knowledge, and actually what I will show in what I will ask in the homework assignment is to actually argue that this protocol, forget about without repetition, let's say, just the one-shot protocol, is also malicious verifier zero knowledge. But let me here try to argue that it's honest verifier zero knowledge. So let's say if the verifier is honest, let me tell you how I can simulate this protocol, why the verifier doesn't learn anything. He can simulate this on his own. And here's how he will simulate it. So he wants to say, look, I can generate this transcript on my own without the prover. So I didn't learn it. What did I learn? A transcript that I could generate on my own. So I really didn't learn anything. How will I generate as a verifier or the simulator? How will I simulate this transcript on my own? What I will do is first I'm going to choose the random edge that I'm going to ask the prover. Only then I would so now first I'm going to choose the edge, then I'm going to choose two random distinct colors to put in safe I and safe J. So I first choose the random edge, then I choose random distinct colors, and I put these distinct colors in safe I and safe J. In the rest of the safes, I don't care. I can put nothing because I'm not going to open them anyway. And then I'm going to open the two safes with the two random colors, random distinct colors. It's exactly the same distribution. What you see here and what you see in actually the real protocol is the same. So in other words, the verifier, he knew he could simulate this on his own because he only got to open two boxes. And he knows that in the two boxes are two random distinct colors. Okay, so essentially, again, with the verifier, the way he simulates this is he chooses two random distinct colors, which is the answer of the prover. He chooses a random edge, and he puts these two random distinct colors in the two safes corresponding to the edge. That's it. Questions?
It seems like you can do this even without knowing a legit coloring.
Exactly. Great point. He can do it without knowing anything. He just needs to know the graph. He doesn't need to know any legit coloring. That's why he didn't learn anything. The verifier doesn't know a legit coloring. He's just giving a graph. He doesn't know the legit coloring. And I want to say,
so the simulator is for the verifier.
Exactly. Exactly. What I'm trying, exactly. So exactly. So what we want to say, the verifier didn't learn anything because the verifier could have simulated this transcript on his own. So the simulator, you should think of him as he's the verifier, right? I want to say the verifier didn't learn anything because he could have simulated this communication. He knew what the prover is going to send him. He knew that the prover, because he knows, okay, first I'm going to get black boxes, then I'm going to get two random distinct colors. So I can simulate this entire thing. I'm going to send a random edge, I'm going to get the two random colors, and now if you want the entire communication, sure, I'll put the safes and put the two random colors in there and give you keys.
And the reason the prover can't cheat is because they give them all of them in advance, and here are the keys to unlock that.
Precisely. The reason the prover cannot cheat is because it's interactive. If he knew ahead of time what I and J is, he could cheat. That would be terrible. But we're using the fact that the prover is talking an interactive protocol. He first needs to get the safes, only then he gets the random edge he needs to open. Whereas the verifier, all he needs to do is look, what does the verifier learn? A transcript. And that's something he could simulate on his own. That's precisely it. That's how essentially we get that's why zero-knowledge proofs are so magical. Because you say, because there's a difference. Like by considering the interactive model, you create a difference between the prover and the simulator, or what the verifier learns. Without interaction, it's just, look, the prover just generates this and the verifier just learns this. It's like in some sense, like the simulator and the prover, if you want, have the same power. The verifier should be able to generate this. How can he generate this? Efficiently. Then it means he can generate a proof efficiently. But here, the verifier and the prover, they kind of play a different game. Because the verifier to say he doesn't learn anything means he can generate this transcript on his own. But the prover, it's important that he does it step by step to get soundness. Any more questions before I move on? You guys have really, really fantastic questions and comments.
I have one more question about the simulator. I'm not quite sure what the role of the simulator is in this zero-knowledge proof.
Good.
Is it just to... Sorry, yeah, that's just a question.
Okay, good. So I want to say that the verifier didn't learn anything. How would I define he doesn't learn anything? I would say, look, the verifier essentially could simulate the prover's answers on his own. He knows if the verifier knew what the prover will tell him, he didn't learn anything. He knew that already. So the simulator is like to say the verifier could simulate. He knew what the prover is going to send ahead of time. And here he indeed knows. He knows that first he's going to get black boxes. And he knows that here he's going to get two random distinct colors with a with the keys. But so to simulate all this, we say, okay, you give the safes, but in the locations ij, you need to put the two random distinct colors, and then you just get random distinct colors. So the simulator, the simulator's role is to say the verifier could simulate the prover's messages on his own, and therefore he didn't learn. If he knew what the prover is about to send, if he couldn't simulate it on his own, he didn't learn anything.
So the existence of the simulator really is to show that the proof is zero knowledge, but not
Exactly.
to prove it.
Yeah, precisely. It's the simulator just shows that the proof is zero knowledge.
Okay.
Exactly right. Great. You guys have very excellent clarifying questions. Okay, any more questions? Okay, so before I move on, I just, one thing I don't like about this is it's still physical. I have these locks, these safes. You know, I want to give you actually just bits. So I don't want to use safes. So in cryptography, actually, we can make these safes digital. And this is also something that I'm excited to teach you of independent interest. This is a primitive that's also the bread and butter of cryptography, and it's called the commitment scheme. So I'm going to replace these digital safes with commitments. A commitment is really what it is. You should think of it as just a digital safe. So a commitment scheme is really just a commitment is just a randomized algorithm, okay? It takes as input the message that you want to kind of hide, you want to put in the safe, and some randomness, and it outputs some value, which is the output of the algorithm, commit of the message and the randomness. Okay, so it's just a randomized algorithm. And the two properties that it has is one, that it's hiding. So if you just see the commitment of the message, you don't know what the message is. Okay, it really hides the message. And the way we formalize it is exactly the way we defined security of encryption. If you think about it, encryption, remember we said it's hiding. It's the exact same hiding we want here, except there's no keys. So what we want, though, is to say that for any two distinct messages, think of them as of the same size, for every two distinct messages, if you see a commitment of M using randomness, or a commitment of M prime using randomness, these two are distributed, may not be the same, but computationally indistinguishable. So a polynomial time adversary cannot distinguish, even if he knew M and M prime. If I choose a random R and give him the commitment of M and R, or I choose a random R, let me call it R prime, and give him the commitment of M prime with this randomness, these distributions look the same. Okay, so even, if he has some information about M and M prime, even if he knows what M and M prime are, if he gets the commitment, the distribution of commitment in M and R, where the distribution is over random R, or the commitment of M prime over random R prime, these look the same. These distributions look the same. So the adversary doesn't learn anything. That's the hiding. The other thing we want, though, is binding, that it's really, a color is in there, you can't change it. Remember, it was very important to us that the prover can't, after he sees the edge, he can't now choose his colors. He needed to commit to the colors ahead of time. So we want the fact that you can only open to one thing. Once you committed, that's it. There's only one M that you can open to. And that's what's called binding. So binding just says that you cannot open to the commitment to two different M's. So there does not exist M, and the opening, the key is the randomness R. So you can't give M and R and M prime of R prime, where M and M prime are distinct, like two different, opening to two different values, says that the commitments are the same. So once you commit, there's only one way to open. There's only one M and R that will give you the value of the commitment. Okay, so that's what a commitment scheme is. I didn't tell you how to get it, but that's what a commitment scheme is. Okay, it's a randomized algorithm where you commit to your message using randomness, and this commitment, it hides, but it binds you. So now you can only open in one way, to the actual message. You can't open to two different messages. Any questions about this primitive? Okay, so now, if you have that, then we're done. Because then what I would do, the prover will just send exactly like before, the same protocol, but we replace the safes with commitments. So we commit to the color 1, commit color 2, up to commit color n. I didn't write it in the slide, but the commitment is randomized. So it's like commit color 1 with randomness 1, commit of color n with randomness n. And when I reveal, I just reveal the randomness. So I reveal color I, color j with randomness I and randomness j. And the verifier just checked that indeed commit of color I with randomness I is what's written in the ith location in the first message. And similarly with j. That's it. That's the protocol. You just use a commitment scheme. That's my zero-knowledge protocol. With soundness, bad soundness, and you repeat it sequentially to get good soundness. Okay, and now what I still need to do is to show you that a commitment scheme exists, because, you know, who said that there's such a thing? That's hiding and binding and so on. By the way, I want to say one thing. If you remember, probably you don't, but if you remember when I started the lecture, I said the theorem said that any proof can be converted into a zero-knowledge one, assuming one-way functions exist. So far, when I talked about the safe, there was no one-way function. Actually, it was a zero-knowledge proof, period. Where's one-way functions come in? It's in the commitments that it will come in. So if you have like real safes, you don't need one-way functions. But once you need to replace the safes with digital safes. For that, you need one-way functions. So any questions before I say a few words about the commitments? Okay, so I want to say a few words about how to generate a commitment. I know that by now you're probably tired because I gave you a lot of information. So I'm just going to say a few words about it because it kind of relates us back to the lecture from yesterday. And the way you construct it is, again, using one-way functions and hardcore predicates. So let's recall what these are. So one-way function is just a function that's easy to compute, but hard to invert. So given x, it's easy to compute f of x, but given y, or given f of x for random x, it's hard to find the preimage. Okay? And remember, we said there's the hardcore predicate theorem of Goldach and Levine that say that every one-way function has a hardcore predicate. I'll remind you of the definition of hardcore predicate in a minute, but let me first tell you what the commitment scheme is. So I'm going to assume what I need is not just a one-way. What I'm giving you today is I'm going to assume I have an injective one-way function. We can construct commitments also just from one-way functions, but it's more complicated. So I'm going to show you a construction assuming we have an injective one-way function. So I have a one-way function, but it's one-to-one. Okay, so now here's my commitment. Let me do a commitment where I commit bit by bit by bit. Okay, I'm going to first commit to like each bit separately. If you want to commit to a string, I'm going to first commit to the first bit in the string, the second bit, and so on and so forth. Okay, so I'm going to show you how to commit to a single bit. And the way I'm going to commit to the bit, this commitment algorithm, what it does, it takes randomness R, it computes f of R, the one-way function applied to R, and then it masks B with the hardcore predicate applied to R. So this is the commitment algorithm, that's it. Now, I'll soon remind you what this hardcore predicate is, but first let's do binding. Why can you open only to one thing? The reason is, because f is injective, there's only one R that will coincide with f of R, because f is injective, and then there's only one B that will correspond to the value, because so you will have to be accepted, you'll have to give B and R such that f of R is indeed, so in other words, f of r defines r, and once you have r, this r defines p of r, and hence b is defined. So you can only open in one way. You cannot open to b and r and b prime and r prime. Why? Because r and r prime must be equal, because they're both equal to f of r. Okay, and it's injective. And hence, b and b prime must be equal, because you will check that the b prime, or the b you have, is your p of r XOR with this value. So there's only one possibility. And that's why it's like binding. There's only one way you can open. And the reason it's hiding, here I'm going to use the hardcore predicate. So if you remember the hardcore predicate, the definition of it says, every one-way function, there's a predicate that if you know the image, the hash value, the function value, there's a predicate that looks random. So somewhere, we said a one-way functions mean you cannot find r, you can't invert, but there's one predicate of r that's really hard, that really looks random. And if p of r looks random, then it's a great one-time pad. Then it really masks b well. And that's why it's hiding. That's it. So for those who didn't follow the construction of the commitment, I think I gave you a lot, so I don't want to completely tire you out here. But what I want you to take out of it from this is that, we saw last time, we saw one-time pad and how we made the encryption reusable using kind of one-way functions and hardcore predicate and so on. Same thing going on here. The way we constructed this commitment scheme is, again, using one-way function, hardcore predicate. We, again, masked kind of using one-time pad. So it's kind of the same techniques going on in both places. Okay, so unless you have questions, I'll move on now to a very kind of high-level, more philosophical part of the lecture. But let me first pause and see if you have any questions. Okay, so what did we do so far? So note, we're only like 1 hour, a little over 1 hour, and I already showed you, I kind of proved to you, it's pretty amazing that I can do it in 1 hour. I showed you that I gave you a zero-knowledge proof for all of NP, assuming we have commitment scheme. And okay, and I constructed these commitment schemes from injective one-way functions. That's great. Okay, but now, in the last 25 minutes, I want to tell you kind of what resulted, like the backlash, like the hoo-ha that the zero-knowledge proofs, the effect they had on computer science at large. Okay? And so now forget about, these zero-knowledge proofs were invented for the sake of hiding, right? For cryptography. We want to hide, we want to give proofs, reveal no information, and so on. But now forget about hiding. I don't care about hiding anymore. We have this new proof model of interactive proofs. That's very interesting because, as I said, for thousands of years, people thought about the concept of proofs, and they never considered the idea of making proofs interactive. So now that we have interactive proofs, maybe we can prove much more. So remember, one of the most important concepts in computer science is this class NP, right? NP is the class of all languages that can be proven efficiently, but proven efficiently using a classical proof. What about proven efficiently using an interactive proof? Which languages can be proven to a polynomial time prover or a PPT, a probabilistic polynomial time prover, given an interactive proof? So maybe if we allow interactive proof, we can prove much more statements. And let me tell you, indeed, that's the case. So with a classical proof, usually classical proofs tend to be very, very, very long. And in particular, we believe that you don't have kind of succinct classical proof that prove correctness of computations of the form, like a program and input x, output 1, within t steps where t is large, like more than polynomial. So usually, classical proofs tend to be very, very long. What I want to tell you, it was soon after zero-knowledge proofs came about, it was shown that using an interactive proofs are much more expressive. We can prove much more using an interactive proof. Let me give you one example of what I can prove using an interactive proof that I cannot prove using a classical proof. So my example is chess. Suppose, here's what I can prove to you using an interactive proof. I can give you a board of chess, and I can prove to you, say that the black player here has a winning strategy. Now note, how can I prove, in order to prove that using a classical proof, the classical proof is going to be really long. Because the only way I know how to do it is to say the following. Okay, no matter what the white player, no matter which move he makes, there is a move for the black player, such that no matter which move the white player makes, there is a move for the black player, and such that no matter what, the black player is going to be accepted. It's going to win, sorry. But I don't know how to give you a classical proof that doesn't not like this gigantic tree. No matter what the white player does, here's the black player does, no matter what the white player does, and look at the bottom, all the leaves are the black player is winning. That's the only way I know how to give you a proof. With an interactive proof, it turns out, I can do it very efficiently, very succinctly. Actually, more specifically, what is known is that the correctness of any computation, any deterministic computation, I can prove it to you, where the time it will take you to verify is similar or proportional to the space that is required in order to do the computation. So if the space is small, like if the space is small, then the verification time is small. And that's the chess example, the space complexity is very small. That's why I gave that example. This is known as the celebrated IP equals p-space theorem. So like with classical proof, you can prove the class NP. That's the definition of the class NP. With interactive proof, you can prove any language in p-space. P-space is all the computations that can be done using polynomial space. So interactive proofs are much, much more powerful. Okay, more expressive. Questions?
So as I understand interactive proofs, we never 100% prove the statement that we want to prove. Then how do we talk about the efficiency of interactive proofs?
So the way you should think about it is I'm happy with, I do know, as long as you're accepted. So I do know as long as you, so sorry, you're asking how do you know if because of the 1/3, 2/3, that's what's bothering you?
Yeah, like the probability that you're cheating.
Good.
The verifier gets lower and lower, but it never gets to zero.
It never gets to zero, right? But as long as you're right. But what I can say is the following: I have an interactive proof for any language in p-space, such that if the statement is false, you're going to be rejected you're going to be accepted with probability 2 to the minus. The probability you're going to be accepted is smaller than the number of molecules in the universe. And if the language is true and you're honest, you'll be accepted with probability 1. You're right that you have a probability of being rejected, but I can make this probability so small that's smaller than the number of molecules in the universe. And for me, I think of that as 0.
Okay.
But you're right, that's the guarantee I'm giving you. But the great question. That's a really, really great question. Any other questions?
Can you restate real quick? So non-interactive proofs, what's the best complexity class, or what's the best you can do with non-interactive?
Good. Non-interactive proof is just NP, the class NP. So NP is really the class that has, the way NP is defined, it's defined as all the languages that if X is in the language, there exists a witness or a proof, right? A witness is a proof that can be verified in polynomial time. So it can be verified by an efficient verifier. So if you don't allow interaction, then it's NP. If you do allow interaction, all of a sudden you jump to p-space. Now, look, NP may be p-space for all I know, but we believe that's not the case. So we believe that p-space is much bigger than NP. Great question. Thank you, guys. These are really, really great questions. I really appreciate it. Any other questions?
Shouldn't we try this interactive proof so many times to understand if we are doing it right or not? I mean, we are talking about time efficiency of this interactive proof. Yes. But my question is that shouldn't we try it so much? For example, for example, about pens, we did the exam so many times. But I think something is echo my voice.
Yes, Mariam, I think I understand your question. Oh my God. Okay. Am I echoing too? No. Okay. So I understand your question. This is a great question. So let me just repeat it because in case because you got cut off in the middle. So I think if I understand the question correctly, you're saying, look, yeah, maybe if you do it once, you're efficient. But I said, oh, you can repeat it many, many times so that the probability of being accepted if you're incorrect, if the statement is not correct, is smaller than, you know, the number of molecules in the universe. You say maybe if you repeat it so many times and get such small error, maybe it's not efficient anymore. If that was the question, then the answer is it's still efficient. Because to get the error, you know, the number of molecules in the universe is that, I don't know exactly, but it's smaller than, let's say, 2 to the minus 500. And to get the error down to that small, you need to repeat the protocol only 500 times. And so you can get, you can get a tiny probability of error while still being efficient. Namely, when I mean efficient, I mean the verifier is polynomial time, and it can verify the correctness of any computation in p-space while ensuring that if the computation is false, if the answer is false, he will reject you. He will accept you only with probability that's smaller than the number of molecules in the universe. Did that answer your question, Mariam? 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 Okay. Wow, it sounds awful. Okay. Any more questions or follow-up questions?
Does the class IP have any bound on the number of rounds of interaction between the prover and verifier?
Good, yeah. So first of all, thank you. The class of IP is the class of interactive proofs. I didn't say that. And yes, so because the verifier is limited to be polynomial time, the number of rounds can be a most polynomial time. At most polynomial. But that's it. It can be any polynomial. So for statements of length n, I allow the number of rounds to be polynomial in n.
Awesome. So then does this, is there a result for, like, can we get interactive proofs with like exponential number of rounds? And then does this result change? Yeah,
so good. So yes, it changes because usually when we talk about proofs, we always think of the verifier as being efficient. If he's all powerful, he can do anything on his own, you know. So we always think of the verifier, he's polynomial time. So everything is kind of up to polynomial, like all the communication complexity can be polynomial, because we always, when we think of proofs, the verifier needs to be efficient. Otherwise, he doesn't need the prover. So the verifier is efficient, and hence we always think of the communication as being efficient. And again, by efficient, I mean, and in theory, when we say efficient, we mean polynomial time. So all the number of rounds is polynomial, the number of bits sent is polynomial, everything is polynomial. Though I do want to say, one can ask, what is the power of interactive proofs where the number of rounds is constant? You know, now is it the same as IP? Is it smaller? And actually, it's believed to be smaller. If the number of rounds is constant, it's the same as only 2 rounds. There's a theorem that shows any constant number of rounds you can collapse to 2. But polynomial you can't collapse anymore. And we do believe that constant number of rounds is not the same as polynomial. But of course, we don't have any proofs because for all we know, NP equals P equals P space. Like we don't, we're pretty bad in complexity at this point. So, but we have strong, conjectures. Okay, any other,
Yeah. Yeah, so when you were talking about the collapsed into the 2 rounds, or talking about the Arthur Merlin protocols?
Yes, Arthur Merlin, exactly.
Okay.
These are known as Arthur Merlin protocols, precisely. Yeah. Okay, so now, so we start with interactive proofs. We said, look, it gave rise to we start with zero knowledge. Zero knowledge gave rise to interactive proof because that's what we needed in order to get zero knowledge. But then we noticed zero knowledge, the interactive proofs are very interesting on its own because they're very expressive, they're very powerful. Forget about knowledge. I don't care about knowledge. I can just prove much more. Now I want to go back for a second to the notion of zero knowledge and just say, shortly after zero knowledge proofs were introduced, remember that we needed one-way functions to get zero knowledge because of the commitments? Shortly after that, they asked question, can we get zero knowledge without any assumption, without assuming zero knowledge? And that motivated them. So apparently you can't do it with just, one prover. And that motivated them to consider another proof system that's called a multi-prover interactive proof. And again, I don't care about the zero knowledge, forget about the zero knowledge, that's just the motivation. But multi-prover interactive proofs are very, very interesting. So let me explain to you what these are. That's kind of the next generation of proofs. So we started with classical proof. We went to interactive proofs. Next generation, also motivated by cryptography, is multi-prover interactive proofs, or two-provers interactive proofs. So what are two-prover interactive proofs? You can have more proofs if you want, but let's consider the case of 2. I have a verifier that's now talking to 2 provers, not just to 1, to 2. And he sends messages or questions to the 2 provers and gets back answers. And what's very important here is that the 2 provers are not allowed to interact. Okay, so before the protocol starts, they put in separate rooms. Each one gets a query or question. They give answers, and based on that, the verifier decides if to accept or reject. And it's similar in the sense that the verifier tosses coins, and we're okay with some probability of error. Okay, for now, think of perfect completeness and tiny, tiny soundness error. So with probability smaller than the number of molecules in the universe, he'll accept false statements. So this was, again, this proof system was put forth because they were able to show that with this kind of proof model, you don't need to make any assumptions. You don't need zero knowledge. You don't need assumptions to get zero knowledge. But again, I forgot about zero knowledge, and I'm asking, what can we do with this proof system? Can we prove more than P space? Maybe we can prove more. And the answer is yes. It was shown that any proof can be made exponentially shorter using a two-prover interactive proof. So in other words, I can convince you that a time t computation is correct while sending questions and answers only of size log t. I wrote here polylog, but actually you can make it even log, order log t. So it's unbelievable, like exponentially shorter. The communication complexity is exponentially shorter than that of a classical kind of proof. And you think, why is it so powerful? Why can you do so much with this proof system? And the intuition is, it's very hard to cheat. It's very hard for these two provers to cheat consistently. Think of suspects. If you have a suspect that committed a crime, if you have one suspect, he'll lie. What are you going to do? He's going to lie. And it's very hard to prove that he's lying. But if you have 2 suspects, you put them in different rooms, now they need to lie consistently. That's much, much harder to lie consistently. And that's exactly that kind of, these two-prover interactive proofs, essentially what the verifier does, he kind of checks consistency against these 2 provers. And he's going to check them. He's going to catch them lying inconsistently. That's really how these proof systems work. What's amazing is that shortly after these kind of multi-prover interactive proofs or two-prover interactive proofs came about, here's a trivial observation. You know, what was noticed is, said, you know what, why do we need these provers then? If the number of queries is only log t, forget about it. Forget about the prover. Have the prover just write for each and every question the answer. There's only order log t questions. So, then the length of the query is only order log t bits. So the number of possible queries is 2 to the length. So only poly t possible questions. You know what? Have the prover write for each and every possible question his answer. There's only poly t questions. Have the second prover do the same. Now this string is big. If originally the classical proof was a size t, now this is a size poly t. I made it bigger. But look at the beautiful thing. So here's a new proof. It's bigger. So you're like, wait, okay. I converted these provers to kind of, these long strings. I'm thinking of this as proof. I just make the proof bigger. Okay, well, what's the benefit? Here's the benefit. I can verify this proof. I can verify this proof by only reading 2 blocks, each of size log t bits. So what this gave you is the ability to write a proof that you can verify. Use reading only 2 blocks of order log t bits each. That's amazing. And actually there's a beautiful, beautiful line of work that led to the fabulous, celebrated, what's called PCP theorem, or probabilistically checkable proof. So what is a probabilistically checkable proof? It allows you to write a proof exactly as we did before, to take any classical proof, make it bigger actually, stretch it a little bit, not by much, by polynomially more. So take a classical proof of size t, convert it into a new proof of size poly t, bigger, but now the verifier needs to read 3 bits. 3 bits. And then he's convinced if you're cheating, he'll catch you with probability 7/8. So you get soundness of 1/8. Of course, that you can't do better because you're reading 3 bits, even if. But anyway, 1/8. And if you want to get better, do more than 3 bits. Do repetition essentially. But what I want to end with, the note I want to end with, listen, look at the kind of the journey. Okay, thousands of years we had classical proofs. Then zero knowledge made us think about proofs differently. Now we say, wait, why are we stuck with classical? Why not use interaction? We can prove much more. And then, why 1 interaction? Let's have 2 provers. Why 1 prover? Let's have 2 provers. We can do more. And this led to this idea. Now what we can do is we can write a proof that to verify it, we just need to read 3 bits. I mean, think how nice it would be if you can verify the correctness of a paper instead of, spending the time to verify it and all the pain, just reading 3 bits of it and being able to be convinced with probability 1/8. So this is kind of, in my opinion, like real magic. I don't know, the fact that you can write such proofs is just mind-blowing. Okay, so let me just summarize kind of the lecture today. So we started with classical proofs. We went to the notion of interactive proofs, start with zero knowledge, but actually, just the model of interactive proofs. Went to multi-prover interactive proofs, which motivated and kind of allowed us to do the probabilistically checkable proofs, PCPs. And then there's more I didn't have time to talk about, but to gain efficiency and so on, there's this notion of interactive PCP, or also known as interactive oracle proofs. And this kind of, this evolution in proofs in computer science. And what's really nice about this, it's really, really beautiful theoretical work. That the way you do these PCPs or proofs is based on really, really nice algebra. And this theoretical work really got, by now, very efficient. And it's, as I said in the beginning, it's used a lot today, and various blockchains, including Ethereum, use these proofs to make kind of their chains more succinct, or to get zero knowledge on the chain. Okay, so I'll end with that. I guess I don't have time to talk about the homework, but yeah, I'll leave it here. I guess you'll go over it in your sessions today. Okay, so thank you very much. I'll stop sharing screens, and I'm here if you want to ask more questions.
I have one quick question. Well, not quick. I'm going to try to explain it succinctly. In the beginning, you talked about that there can't exist a true zero knowledge proof without asking many times. Does that mean that, let's go back to like the tricolorability example. Does that mean there can't exist a one-way function that somebody who knows the proof could calculate some value that the verifier would be able to say the only way they could calculate this value is if they knew a true tricoloration of the graph, or without revealing?
Sorry, can you say it again? Sorry, can you say it again? Your question? I got lost.
Is it possible to have a one-way function that you could calculate for, say, a tricolorability, like a checksum, let's call it that, where it verifies, it's a certificate that you know the answer, but it doesn't reveal the answer at the beginning. Is that not possible then?
Yes. So let me tell you what you can do. Well, I said you can't have just a certificate. Let me tell you, today when we use zero knowledge, they are non-interactive, but the model is different. I didn't get into it in the lecture, but what we can do is something along what you're saying, which is if we have we agree on some common random string. You can think of the common random string as like a seed to a function in a sense, but if we have some we call it a CRS, some common random string or a common reference string that we all agree on, then we can make the proof non-interactive. But soundness then holds still, but then soundness holds kind of computationally, it's more complicated. The answer is complicated. Either soundness holds computationally or the zero knowledge holds computationally. But what's important is that you can do it if you have some CRS, some common random string, or reference string, and it's that common reference string is of the form of this one-way function that you're talking about. So you can do it, but again, it's a slightly different model. Any other questions?
We had one question in the chat, which was along the lines of, so have zero knowledge proofs been used in maybe real life interactions, like a judicial system or anything like that?
Okay, so first of all, it's used, you guys use it anybody who has an iPhone or anything like that, the most common digital signature scheme. I didn't talk about digital signature, but there's such a thing called the digital signature, and the most common digital signature scheme used by all iPhones or used in the blockchain or in many, many places are based on zero knowledge proofs. So we do use zero knowledge proofs all the time in digital signatures. I think that's probably the most common use of zero knowledge today. Any other questions?
Sorry, I have a question.
Yeah.
In the zero knowledge model, the prover sends out some boxes that are locked, and then sends out some keys to verify his answer, right?
Yes.
What if we're gonna do it securely? We don't want anyone else to eavesdrop on the boxes or gain any info on them.
Good, great. So what you do, so good. So if the prover and verifier don't want people to see what they're proving to one another, maybe the verifier said, I don't want people to know that I want a proof of this, a certain proof. I don't want people to know that I'm interested in that proof. That breaches my privacy. Then what the prover and verifier would do, they will do all their communication encrypted. So they're going to encrypt, well, you can't encrypt the box, but the commitments. So essentially everything is going to be encrypted.
So we just encrypt it like the normal way and communicate over that.
Precisely. Great question. Exactly. I like that question. It ties us back to previous lecture. Yes.
Okay, thank you.
Any other questions? Okay, guys, thank you so much. I really enjoyed teaching you. I hope I convinced you that cryptography is amazing. I hope to, see you guys soon and for you to help us advance the field forward. Thank you.